Okay, gang, welcome to our next lecture of computer graphics. Yeah, it is computer graphics. It took me a moment to remember what class I'm, I'm teaching today. So I wanted to start out by bringing your attention to, well, two things. One, the programming assignment that we did yesterday. Everybody did their meetings with me. I thought those went well. For those of you who've had me before, it was no big deal. For those of you who are new to me, I know it's kind of nerve-wracking the first time you have to meet one-on-one with the prof and talk about your programs, but hopefully you guys got to see that it's not scary. It's not that big a deal, and you know, and hopefully it wasn't too bad. The most common problem was the rotation bug. I would say about a third of you ran into that. And if you met with me early in the morning, I may not have talked you through that bug, but by about 11 o'clock in the morning, I was seeing enough of it that I had discussions with everybody. Basically, in the rotation functions, some of you were modifying an X value or a Y value and then using that modified value in the next equation. So like in Z-axis rotation, you would compute a new X, and then when you went to compute the Y, instead of using the original X as an input, which you should have done, you were using the modified X. And if you do that, what happens is as you rotate over and over and over, you'll begin to deform the polygon. So that needs to be fixed. You know, there were a bunch of other little things that I found in programs. I tried to bring that to everyone's attention. And the point that I tried to make is, because each of your programming assignments, 2 builds on 1, and 3 builds on 2, and 4 builds on 3, those 4 programming assignments, which is over 3/4 of the course, right? It's all building on one another. So you got to go in it with a different mindset than normally when you write a program. Normally you write a program, and if there's a bug, you know, you try to futz with things to fix the bug. And if you can't really figure out what it is, you just do things to hide the bug, right? So the prof won't see it and you'll get a higher grade. But that's totally the wrong way to go about this. A hidden bug is actually worse than a bug that's visible. And so a lot of people had things like they screwed up their projection equations, and so then they went in and they, you know, would change their translation equations so that left and right would appear to work right, rather than solving the problem and figuring out, well, why are Mike's formulas, you know, not working properly. And if you just go in there and start diddling with things to try to patch it up, well, that might get you through assignment 1, but then you're going to have 2, and then you're going to have 3, and then you're going to have 4, and these things can build on one another. So anyway, that's the programming assignment. The next thing that I wanted to do is I wanted to talk briefly about the syllabus. I uploaded a slightly revised syllabus. I decided to change the due dates for assignment 4 and assignment 5, and you might say, but Mike, we haven't even, you know, gotten assignment 3 yet, you know, or so what's going on here? Well, I've been trying to work out my lectures over the next 2 weeks, and I needed a little bit more time before assigning assignment 3. Okay, so you're working on Monday. Today's Wednesday. Monday, I gave you guys assignment 2, right? And assignment 2 is due. That hasn't moved. It's still next Thursday, a week and a day, a week from tomorrow. And that's fine that it's just a little over a week, because assignment 2, if you've got assignment 1 working, isn't bad at all. But assignment 3 and 4 are the more difficult ones. So basically what happened is assignment 3 used to be due right here on the 28th of January, sandwiched right between the project midpoint presentations. And I decided that was really, I don't want you guys rushing to get assignment 3 done at the same time you're rushing to get your midterm project presentations done. So I moved it a week later. So basically what I did is I pushed out giving off assignment 3 by, normally I would give it out, you know, on Wednesday or on Friday, but I pushed it out to that Monday. And you should be able to get started on it about right after Martin Luther King Day. And you'll still have 2 weeks, really 2 weeks and 1 day to get assignment 3 working. And that meant that I had to push back assignment 4 as well. What I did there for assignment 4 is I'm giving it a little later, right? Because I pushed it back. So it's a week later, but I bumped it a week later too. So used to it was due right before Mardi Gras. And I went, well, screw that. I doubt there's going to be much Mardi Gras this year because of COVID. So I moved it to be due the day after we get back from Mardi Gras. And in years past, I hadn't really done that because I'm like, I'm going to ruin their Mardi Gras. But Mardi Gras is already ruined this year. So by doing that, it'll give you 2 full weeks to do assignment 4. Okay? So really from assignment 3 being given to assignment 4 being due should be almost a month, from the 20th of January to the 18th of February. And 3 and 4, I mean, 4 builds directly on 3. So I'm giving you guys more time there. And then assignment 5, obviously you're paying that price with assignment 5. There's less time, but assignment 5, I'm going to give you guys a go-by program, and quite frankly, it's more like, I mean, it's harder than assignment 1, but you're going to be given a go-by program that you will essentially have all of the equations implemented in it, and you'll just be taking an old program written in a dead language and transcribing it, and making some modifications and tweaks, which make sure that you understand how the program is working. But it's not nearly as big a deal as either assignment 3 or assignment 4. So we can give up some time there. I think this is going to work better. It's not gonna have a programming assignment due right when you're working on your midterms, and I'm giving you more time actually to work on both 3 and 4, because now the Mardi Gras holiday, instead of 4 being due immediately before Mardi Gras, it's due immediately after. So I think this is going to work better for everybody by spreading things out a little bit, and hopefully the extra time will make it possible for for you guys to do better on the assignments. Also, too, as I'm sure you've seen, the lecture notes are evolving day by day. I spent a lot of time over break, creating these notes. What I'm doing is, normally what I do is I hand out physical handwritten copies of notes that I've generated over the decades, and we go over them in class. Well, because everything's online, I mean, I could have taken images, scans of them, and put them up, but I thought, well, crap, COVID is a good excuse to actually reorganize everything. And so I've been a busy beaver reorganizing everything, but hopefully the result will be that the notes are more clear and the algorithms, especially for programs 3 and 4, are more clear. So hopefully it will be much easier for you guys to implement those programming assignments than we've had last year. So what I'm hoping is by spreading things out, reorganizing the notes and making the examples more consistent, that you will actually be able to do assignments 3 and 4 much better, much more easily, and also that you'll get higher grades. That's what I'm hoping, right? So anyway, that's what we're doing there. Are there any questions before we dive into the lecture today? No. Okay. So here are here's where we stand as far as the notes are concerned. We're about to start talking about matrix notation. I gave you guys just a little bitty taste of that at the end of lecture on Monday. But this is what we're going to be talking about today. We're going to be talking about homogeneous coordinates, matrix notation for 2 and 3D. We're going to be talking about a number of various mathematical conventions. Basically, I'm going to be showing you different ways of implementing the transformation equations that we've already covered, okay? Because there are different ways of doing that. And even so, and most of them involve matrices, but even when you're using matrix notation, the actual matrices, the details of those matrices will depend on whether you're using a left-handed or right-handed coordinate system, and it's going to depend on how you're using those matrices. So basically, what I want to do is when you go and you Google rotation or something like that, different things are going to pop up. And you'll look and you'll say, well, this thing is different from this other thing, which sort of, this has a minus here, this has a minus there. Did somebody goof up? Why is it different from one source than another? And they're different because different authors make different assumptions. We're using, for example, a left-handed system, right? Where left-handed because the Z goes out away from us. A positive Z goes into the distance. That's what's used in DirectX or in Direct 3D now, okay? But if you use OpenGL, OpenGL uses a right-handed system. So the equations will be slightly different. And our rotations, well, we define them counterclockwise, looking from, and we're going to talk about this a little more, counterclockwise looking from the negative point on the axis. Well, other people define it clockwise when viewed from the positive side of the axis. And all of these are just arbitrary decisions that somebody made somewhere, and different systems use different assumptions. And so the math is slightly different. I mean, it all works out the same, but it's slightly different. And so if you start pulling stuff from different sources and start gluing it together without a deep understanding of what's really going on there, you can screw everything up. Because some things are thinking, oh, well, this math works if it's left-handed, but this other math in your program works if it's right-handed. So you just can't go out and start pulling things from sources and Googling like you can in other areas. And I think that's one of the reasons why students sometimes run into problems in graphics, is because there's half a dozen different ways of doing things. And if you start Googling, you'll get different pieces from different ways with different assumptions, and so you'll end up with a hot mess is what you'll end up with. So we want to talk about what the assumptions are, okay? All right, so let's pop back down into, hold on. So yeah, let's pop back down into this and we get going. Again, if there are any questions, feel free to ask them. And sorry, this is a PowerPoint, but it doesn't really matter. Okay, so here's where we are. We were doing the transformation equations. Okay, so the first thing we're going to do, if Mike can stop scrolling, the first thing we're going to do is I'm going to introduce something called homogeneous coordinates. You might say, well, what are homogeneous coordinates? Well, normally when we have a two-dimensional system, we have an X and a Y, right? So you have an ordered pair for a two-dimensional system. If you've got a three-dimensional system, you have an ordered triple, an X, a Y, and a Z. Well, in homogeneous coordinates, you're going to add a 1 at the end of your coordinates. So if you've got, for example, you know, a two-dimensional system with an X or a Y, that's going to become XY1. And if you've got a three-dimensional system with an X, Y, and Z, well, that's going to become XYZ1. Now, you might say, well, why are you adding this 1, Mike? That just seems dumb. Well, I refer to this as a representational tweak. It's not going to change anything. It's just that you'll have a 1 at the end and you'll just ignore the 1 when you plot things, right? Okay, all right, Mike. If you want to add a 1 at the end of everything, you can add a 1 at the end of everything and just ignore it. Okay, great. But that seems like a really silly thing to do. Okay. But actually, it's a really smart thing to do because it's going to enable us to be able to represent all of our two-dimensional equations using a 3x3 matrix, and it's going to allow us to represent all of our three-dimensional equations with 4x4 matrices. And we'll be able to recast all of our equations using matrix notation. Okay. Now, what do you mean by this, Mike? Well, let's focus to begin with on two-dimensional because they're a little simpler. And let's think about our two-dimensional translation equations. Well, ignore this crap in the middle, but X translated is the original X plus a translation factor. And Y translated is just Y plus a translation factor. And in case you were interested, 1 is equal to 1. It doesn't hurt to say 1 is equal to 1. It's telling you something you already know and something that's not very germane, but it's true, and you could say 1 equals 1 if you wanted to. Well, these equations, X translated is the original X plus the translation factor in X, and Y translated is the original Y plus the translation factor in Y, and 1 is equal to 1. These three equations are what you get if you do this matrix multiplication. So this matrix right here, right, is the 2D translation matrix. Why? Well, again, in case it's been a little while since you played with matrices, I've got a 1x3, right, which I'm multiplying times a 3x3, 3 rows by 3 columns. Well, a 1x3 can be multiplied by a 3x3 and gives you a 1x3. So row 1 multiplied by column 1. So X times 1 gives you X, plus Y times 0 gives you 0, so you can ignore it, plus 1 times TX gives you TX. So you end up with X times 1, Y times 0, plus 1 times T of X, so the translation factor in X, and that simplifies to X plus T of X, right? X plus the translation factor in X. So that's where this first equation comes from. If you take the first row and multiply it times the second column, you'll get YT, the second term, and that'll be x times 0, which is nothing, y times 1, which is just y, plus 1 times t of y, which again is the translation factor in y. So y translated is just y plus the translation factor in y. And finally, first row times the third column, right? X times 0 is 0, y times 0 is 0, plus 1 times 1 is 1. So that's why 1 is equal to 1. And so we haven't changed our equations at all. If you do this dot product, right, doing the dot product is these operations, which means that this matrix, if you take a point and you multiply it times this matrix here, you will get exactly the same answers as if you use the formulas that you coded up in your program. Does that make sense? Well, in the 2D version, we'll look at the 3D version here in a minute. Does that make sense? Somebody say something in chat. I got one yeah. There's one. If I have reached 1 out of 18 people, I don't know why there are only 18 people here. There ought to be 25 people here. Okay, good. Okay, so then what about scaling? Well, here's the two-dimensional scaling matrix. And the S's are, the scale factors are along the diagonal. So for the translation factors are along the last row. For the scaling, it's the main diagonal of the matrix. But if you do the math, right, if you multiply this 1 by 3 times this 3 by 3, you'll get this 1 by 3 over here. And if you look at what you did exactly the same math that gives you x scaled is x times s of x, because x times s of x plus y times 0 plus 1 times 0. That's how it works out. So you haven't changed anything. If we look at our two-dimensional rotation matrix, it looks like this. Cosine, cosine, sine, sine, with the negative on the first sign. If you multiply it out, you'll see that if I multiply first row times the first column to get my rotated x, it's just the exact same equations that we've already talked about with the added notation at the end that 1 equals 1, right? Now you might have said, but Mike, couldn't I have do I really need 3 by 3? Couldn't I use a 2 by 2? Well, you could have used a 2 by 2 for scaling and a 2 by 2 for rotation, but then that would have screwed things up. You wouldn't be able to do translation with the same size matrix, because translation uses the final row, okay? You might say, well, why are you obsessed with 3 by 3 matrices? Well, if you make everything the same dimensionality, right, the same size, I guess I should say, then you can always multiply these matrices together to get what are called composite matrices, and we'll talk about those in a little while. 3D works exactly the same way, except you've got an extra dimension. So now then the translation, it's a 4 by 4 matrix, and it's translate X, translate Y, translate Z. Multiply it out, and you get exactly the three-dimensional equations that we had before, and you get at the end 1 equals 1, which is correct. You can ignore it, but it's correct. And then the scaling, stop that, Mike. Scaling is the same sort of thing. The scale factors are along the main diagonal. You do the multiplication, and you get the same equations with the 1 equals 1 tacked on to the end. Now, rotation in 3D is a little different because you've got 3 cases. You have the rotation around Z, the rotation around Y, and the rotation around X. The Z-axis rotation is exactly the same little matrix that we saw before, right? If you look at the first 3 rows and the first 3 columns, this is exactly the two-dimensional matrix that we had for rotation. but you just add another row and another column. Everything's 0 except a 1 here at the bottom. Multiply it out, and you get exactly the same equations. And remember, for a z-axis rotation, the z is unchanged. So again, z-axis rotation is really the same thing as the two-dimensional case, really. It's just that you don't change the z. And again, this is exactly what you guys implemented in code, right? Exactly what you implemented in code. And but now we're just saying, well, you can do it through a dot product where you use this matrix. When you're thinking about rotations, it is important to think about the direction of rotation. If you remember the way we defined z-axis rotation, it was in a left-handed system, the system that we're using, it was a rotation that was counterclockwise. In other words, from plus x to plus y, when looking along the z-axis towards the origin from 0, 0, minus z. What are you saying here, Mike? Well, okay. I'm going to turn around like this so you guys are looking at my fingers from the same way that I'm looking at my fingers. My thumb is x. My thumb is pointing into positive x. This is y. It's pointing up and towards positive y. This is my left hand. See, it makes an L. If you're dyslexic like me, that helps you remember that it's a left-handed system. And z is the direction that this finger is pointing, so it's pointing into positive z. My fingers keep vanishing. So when we did a rotate, we defined it as going from positive x towards positive, my fingers are vanishing, from positive x towards positive y. So it's going counterclockwise when viewed from, where are we viewing it from? We're viewing it from 0, 0, some distance in minus z. So when viewed, the z-axis rotation, the way we've defined it in a left-handed system, is from, like I said here in the notes, from in a left-handed system where positive z is going away from us, right? We're viewing things from 0, 0, minus z, so in negative space, looking towards the origin. It'll be a counterclockwise rotation from plus x to plus y. Does that make sense? Now, different authors might define this different ways, and if they do, what will happen is the signs will flip, and we'll talk about that in a moment. The sign of the signs, you may pull up a matrix. If you did a Google search on z-axis rotation, you may pull up a matrix that has a positive sign here and a negative sign here. Positive. It's possible. It depends on the assertions that your author, the person who wrote that matrix, was making. And so just because you run across that in the literature somewhere with the Google search, don't say, "Oh, Mike made a mistake," because it depends on what the assumptions are. And yes, Mike makes mistakes. And if you find something that seems weird, ask me, because maybe I did make a mistake. But what I'm saying here is there are no mistakes in these matrices. These matrices are defined correctly for the system that we have, but other authors will have other systems, okay? So don't get shocked if you see something else in the literature. Now, what about the y-axis rotation, okay? Well, the y-axis rotation looks like this, and it's still cosine, cosine, sine, sine, right? So this little, I guess you can think about it as a little cross here, or a little X with cosine, cosine, sine, sine. That's going to be the same, but you'll notice that instead of the negative sign on the sign being down here, the negative sign on the sign is up here. Basically, if you do the cosine, cosine, sine, sine, where you put this negative, either here or here, affects the direction of rotation. You flip it, you'll flip the direction of rotation. But the way we've got this defined here, you multiply it out and you get exactly the equations that you implemented in your programming assignment that you guys went over with me yesterday. Now, how is it rotating? Well, again, in a left-handed system where positive z faces away from the user, the z is moving away, it's pointing away from you. You're looking at things we need to talk about it's a left-handed system, z points away from the viewer, right? But we're talking about, okay, this is going to be a rotation around the y-axis, but in what direction is it going to be, okay? Well, asking or specifying the direction of rotation, it only makes sense if you're talking about where the user is. So we're doing here now a y-axis rotation. So a y-axis rotation will appear counterclockwise when you are looking up, right, along the y-axis. It's the y-axis rotation. Y is the vertical axis. So now, right, so you can see. So now we still have our left-handed system, right? But we're doing a y-axis rotation. This is our y finger, right? This is our x finger. This is our y finger. That's our z finger, right? So we're going to be doing a y-axis rotation. Positive y is up here. Negative y is down here. Just like when we did the z-axis rotation, and I said, okay, we're going to be looking from minus z towards the origin, and that's why it's a counterclockwise rotation from x to y. Well, now we're going to be looking from below, looking up, okay? So we're here in minus y, looking towards the origin, and what's going to happen here? Well, we're looking up from minus y, and that's going to give us a counterclockwise rotation from z to x, because we're down below, if you can see this. Think about, do the same little dance I'm doing here with your hand, okay? So we've got our system. I'm down below, right, looking up, and I'm doing a y-axis rotation, so it's going to go from positive x to positive z, and that will be from x to z. That will be counterclockwise when viewed from below, okay? All right, so that's y-axis rotation. How about x-axis rotation? Well, now we're going to rotate around the x-axis, which means we're rotating right in the zy plane. Again, we're still using our same left-handed system. Z still points, away from where the user will be in the end. This is going to be a counterclockwise rotation from positive y to positive z when looking sideways along the x-axis from a point along the negative side of the x-axis, minus x, 0, 0, looking towards the origin. So it'll be counterclockwise when you're looking from minus x towards the origin. Here's the matrix. Again, it's got that same cosine, cosine, sine, sine will cross here. You put zeros everywhere else except ones along the main diagonal. And you always do that. If we go back, you do your little cosine, cosine, sine, sine. Everything else is zeros except for a 1, always in this corner, and another 1 where your rows cross. So our 0 rows crossed here, so that's why we got a 1 there. They crossed here, so we got a 1 there, and if we look here, they crossed there, so we've got a 1. Okay, it's real easy to construct these matrices from from memory, because all you got to remember is, okay, cosine, cosine, sine, sine, and then you got to remember, okay, for z, they're up in the corner, and then as you go for y, they break apart. You've got a row and a column between them, and then when you get to x, they're clustered in the middle. So you can recall these things from memory pretty quickly. So that's our rotation matrices. And again, I give the equations, and for x and for y, I also work through an example of a 90-degree counterclockwise rotation, and I do that so that you can see that you end up with a point that is so here's our point 0, 0, 1, right? So that's x is 0, y is 0, z is 1. So that's 1 unit into the positive z. And if we do the rotation, that'll go from positive y to positive z, right? You end up with well, actually, this is a typo. I do make typos. Sorry. So it's 1, 0, 0, and so that's our input number. And it becomes 0, 0, 1 because we moved from positive y to positive z. And I'm still doing that wrong, from positive y to positive z. I need to go back and look at the numbers on this one. I'll fix it after class when I can think about it. But we're going from positive y to positive z. So I need to play with this. So let me mark it in red so that I get the math right on that. Font? No, not font. Color. Let me examine that after class. Let me check on this one. This one was from positive z to positive x. Oh, I'm reading it backwards. I'm such a dyslexic. This is the input, this is the output, which makes sense, yes. So from z to x, so 0, 0, 1 is the input, right? We've got a 1 in z, and it'll flip it so that you get the 1 goes into x, so that was correct. Let me go back and look at this. The input, yeah, let me reset it. I should read what I have written rather than immediately start going, oh, you made a mistake. Because here's the input, right? You got a 1 in y, and that goes from y to z, so you get 0, 0, 1. So everything's good. There is no mistake. It's just Mike can't read. That's the mistake. So again, with this input, 0, 1, 0, a 90-degree counterclockwise rotation when viewed from minus x, okay, a point minus x, will give you 0, 0, 1. And so you can see that the output is 0, 0, 1 when the input was 0, 1, 0, 0, 1, 0. Okay? So that is, and what I'm really doing here is I am the x, the y, and the z here in this equation is the 0, 1, 0. That's where they plug in, and that's why you get a 0 here, because 0 times 1 is 0, 1 times 0 is 0, and 0 times z is 0, right? Or 0 times 0 is 0, plus 1 times 0 is 0. So that's why the x comes out as 0 here. Taking this and plugging it into this equation, right, will end up also giving you 0. Plugging in the 0, 1, 0 for x, y, and z will give you a 1, right? Will end up giving you a 1 here. Okay, so that's the so that is the matrix form of these equations, and I tried to go through and give you an example that shows you that yes, they are moving from the axes that I specify, which means that the directions are counterclockwise when viewed from the negative point on the axis. But notice these other little things I say here. Well, if it's negative, if it's counterclockwise when viewed from negative x, 0, 0, then it'll be clockwise when viewed from positive x, 0, 0. And the same thing here. This was counterclockwise when viewed from minus y. It'll be clockwise when viewed from positive y. And going back to our z-axis rotation, right, we define the z-axis counterclockwise from negative z, where we think of the eyeball usually being. But if you flipped things around and looked at it from positive z towards the origin, this would also flip and become a clockwise rotation. I don't make that note here, but it's just as true as the other ones. So if you flip where you're looking from, it will flip the direction of the rotation. So why am I making the big deal about this? Because if you read the direct 3D documentation, they use the same matrices I use, and they work in the same way that these matrices work, but they will describe the rotations as being clockwise because they are assuming that you're looking at the origin from a positive point on the axis, rather than I'm doing it from a negative point on the axis. Why am I doing it differently? Because if you think about when you do the projection and you actually look at the system, you're looking from negative z, right? It will be a counterclockwise rotation. Look at your code, run your program and see how it works. When you press the positive z rotate button, the thing will move counterclockwise from positive x to positive y. It's doing that because you're in minus z, okay? Well, to be consistent, I said, well, let me attack x rotation and y rotation from the same minus region of the axis to keep things consistent, okay? So they're trade-offs. That's why different people do these things different ways with different assumptions, because you know, it seems kind of weird to talk about looking from something from minus. You know, why aren't you looking at it from positive? Well, because in a left-hand system, when you do your projection, you're going to be looking at it from minus z. So why not treat the other axes in the same way, where you're looking from the minus position? Okay. So this maybe will clear a little bit of that up. Left-handed versus right-handed coordinate systems. There's no one way of doing it. Like I said, DirectX and Direct 3D use a left-handed system like we're using in this class. OpenGL, which is another graphics library system that's popular, uses a right-handed system. So it's exactly backwards from what I'm telling you here, right? And if you start looking in OpenGL, you might go, well, Mike has his minuses in all the wrong places. No, he doesn't. They're using different assumptions. You can, if you want, I've actually put a link to some Microsoft Direct 3D documentation that has the transformation for rotate, and you'll see that they are exactly what we just covered, okay? But again, if you look at OpenGL, it's going to be different again. So what I tried to do here is I tried to say, okay, so let's go back and take the z-axis rotation, the first one that we looked at. What is it doing? Probably the best way, instead of talking about is it counterclockwise or clockwise, because that's going to depend on where the viewer is, the best thing to say about it is this matrix, when you take a point and you multiply it, this matrix, it's going to do a z-axis rotation from plus x to plus y. That's what it always does. Now, how a movement from plus x to plus y looks depends on where you are. Are you in negative z or are you in positive z? And it depends, are you in a left-handed system or a right-handed system? So I tried to lay out all the cases. Here's the standard case that we're using in this class. We're using a left-handed system. We're looking for minus z, so a z-axis rotation is counterclockwise. If I were to move, it's still in my left-handed system, but I moved over to the other side of the axis and I'm looking towards the origin from positive z. I'm now in the object space, but I'm looking towards the origin from positive z, still in a left-handed system. You're always moving in this with this matrix from plus x to plus y, so now it's a clockwise rotation. Well, if I flip to a right-handed system and I look at it from positive z, well, that's going to be a counterclockwise rotation. But if I'm in negative z in a right-handed system, it's going to look like a clockwise rotation. So these are four different ways of saying the same thing. This matrix will rotate in z, moving points from plus x to plus y. Does that make sense? And why am I straining over all this? I'm straining over all this because you might read four different things in the literature, and they're just four different ways of saying the same thing, okay? And I don't want you to get hung up. Really what's happening is things are moving. If you put a point on plus x, so 1, 0, 0, right? 1 in x, 0, 0. It will become, with this matrix, 0, 1, 0. You've moved from plus x to plus y. That's what it does, okay? And similarly, if I flip the signs, I wrote this in red to show you that I'm flipping the sign of the sign, right? So now then, it's going to all work backwards. You're going to be going from plus y to plus x, okay? So 0, 1, 0, right, will become 1, 0, 0. And it's always, with the sign up here, it's always plus x to plus y. Whether it's counterclockwise or clockwise depends on whether you're in a right-hand or a left-hand system, and it depends on if you're looking from a negative position along the axis or a positive position on the axis. Does this make sense? Does that make sense? I see some nodding heads. Let me look at some of my peoples. I see some of them looking bored. I see some of them nodding their heads. Okay, good. I don't see anybody who seems like they're just totally lost. So that's good. Okay. Sorry if that was beating a dead horse, but what I'm trying to do is I'm trying to make sure that you guys don't get confused when you read other things in the literature. That's what I'm trying to do. Okay. Now, so we were talking here in this section about left-handed versus right-handed systems. Let me make your life even more complicated. This section is called mathematical conventions. So one mathematical convention is whether you're using a left-handed or a right-handed coordinate system. Okay. To make things more fun, when you are using matrices, You can say, well, I'm going to take a point and multiply it times a matrix, right, to give me a point as a row matrix, essentially. And this is the way that I've been showing you everything so far in today's lecture about matrices. But you can just as easily compute the X, Y, Z as a column matrix if you take a matrix and multiply it times a point as a column. So here we have a 4 by 4 times a 4 by 1. Well, that will give you a 4 by 1. So this is the same math, okay, as this, exactly the same math. It's just that I'm doing a point times a matrix here, which gives me my X, Y, and Z out linearly in a row, which is what we're used to seeing it. Or I could do the same math by taking the matrix times the point, but we express the point as a column. If you do that, your same answer will come out, but it will come out in column form. Now notice what happened. The matrix went from having the translation factors be along the bottom row to being along the left column. So sometimes if you look up three-dimensional matrix, right, you look up 3D rotation, you'll see a picture of this matrix. Why? Well, because they're assuming, and I can do a Google search while we're doing this, and you'll see, because this matrix shows up, and sometimes this matrix shows up. But then only in isolation, you might say, well, why is some people showing it this way and some showing it this way? It's because you have to read the details of where the image came from, right? And you'll see, oh, if they're doing it this way, it's a point times the matrix. If they're doing it this way, it's the matrix times the point. Okay, so it's quick and easy to see. I mean, if you see T along the bottom, you know, oh, it's point times matrix. And if you see T along the column, you know, oh, it's matrix times point. But what about scaling? Scaling is going to look exactly the same. It's still going to be S's along the main diagonal. If you do the math out, you'll see that this and this produce exactly the same X, Y, and Z. Okay? When we get to the rotations, things get a little bit more subtle because all that happens is the sign of the sign flips. You might say, wait a second, Mike, you were just talking about the only difference between a left-handed system and a right-handed system rotation, whether it's going to be left or right, is moving this sign. Yes, that's true. But another way it can flip is if you're going between point times matrix or matrix times point. So now then, if you see this matrix here, okay, if you just see the matrix, you don't see anything surrounding it, you just see the matrix, it might be assuming a counterclockwise rotation in a left-handed system, but it's in matrix times point form. Or it might be in point times matrix form and it's assuming a counterclockwise rotation in a right-handed system. Isn't this all wonderful? Is there any difference in efficiency with these? Absolutely none. It's purely a difference in notation. And all I'm going through this because, look, when I tried to teach myself this stuff, right, I was like so confused because I'd look in one book and there would be this matrix, and I'd look in another book and there would be this matrix. And I'm like, why are the matrices all different? And then I started reading more and looking at it and go, are they changing the equations? Well, and then you had to say, oh, well, they're using a left-handed system. Oh, they're using a right-handed system. Oh, they're using point times matrix. Oh, they're using matrix times point. So I'm coming up with a consistent way that we're doing it in this class, but I'm taking the time out here in this section to say there are other ways of doing it. They're just as correct. Direct 3D uses one way. OpenGL uses another way. You just need to know that there are different ways of expressing these things, and you need a deep enough understanding to know that we're not changing the underlying equations between these two formats. They're just a notational difference. And if you did want to change the direction of a rotation, you do flip the sign of the sign. Okay? Exactly. At least it's not going to be on a test. Now, I did want to prove, because I'm so bad at math, I have to prove everything to myself, and so I want to prove it to you too. I take the Z case and I show the computations. Green is showing the computations if you're using point times matrix, and blue is showing the computations if you're using matrix times point. And you see that the green computation and the blue computation give you exactly the same as the formula that I've given you guys. So there's no, it's just a notational difference here, okay? And again, this is to do a left hand or counterclockwise rotation when viewed from minus Z in a left-handed system. In other words, from plus X to plus Y, okay? If I wanted to go the opposite direction from plus Y to plus X, this sign would change. The minus would go here in this version, and the minus would go here in this version. Does that make sense? Okay, so the matrix you're using depends on a bunch of things. Is it matrix times point or point times matrix? Is it a left-handed system versus a right-handed system? Is it a counterclockwise rotation versus a clockwise rotation? So they're kind of like three different variables, and they can all be different. Okay. Why matrix notation, Mike? With all of this complexity, why are you doing this to me? I never did anything evil to you. Why are you being evil to me? Oh, I'm not. Because remember, you can always use the equations which you're using in your code. And like I say, some of you will decide that you want to switch over to matrix notation and will by hand implement the matrix multiplications. That's good. If you want to do that, that's fine. Others of you will just stick with the equations. That's fine. Doesn't matter. We don't have any special purpose hardware, so there's no real reason for you to move. Well, there's one reason, but it's not at the level of complexity that we're writing our programs. The equations are just as good as doing it in matrix form. So why are we studying these matrices if we're not going to use them in our programs? Well, there are three things. There are three reasons to use matrix notation. The first one is matrix notation allows for parallelism. If you think about the first programming assignment, one of the errors that about a third of you made, and even those who didn't make the error, a number of you said, oh yeah, I ran into that problem, but I've discovered it and I fixed it, was that you're doing the two rotation, the z-axis rotation equations, and like we talked about earlier, you compute a new x, and then when you get to the second equation, you're supposed to use the original x, but you've changed it, and so you're using the wrong value there. Well, the deal is you're doing those two equations sequentially, but they're independent, so they could be done at the same time. And that's really what performing matrix operations allows you to do. It allows you to compute everything in parallel. Let me go back and say that again, okay? Z-axis rotation. The computation of X rotated, Y rotated, and Z rotated are totally independent of one another, right? You get the the X rotated value here by taking this row and multiplying it times this column. That in no way impacts computing Y, which is taking the same row and multiplying it by the second column, which in no way affects the computation of Z, which is taking this row and multiplying it times this column. Okay? So that's why matrix multiplication hardware is built to do the dot products, the matrix multiplications in parallel, because you can speed it all up. You can do all of those calculations at once, rather than the way that if we're doing it through equations, we have to do 3 equations one after the other sequentially. And that takes 3 times as long, right? So that's the big reason why we're using matrix notation. Is in matrix notation, you can create special purpose hardware, GPUs, graphics processing units, TPUs, tensor processing units. Tensors are just matrices with a couple of extra little thingies, a couple of extra little restrictions. They're matrices. So GPUs and TPUs are built to do matrix operations in parallel. Does Python have functions to run programs in parallel like MATLAB? There are, that's a question that I've not looked up the answer to. I am sure there are libraries that allow you to do calculations in parallel. In fact, I know the answer to that's yes, because if you look at TensorFlow, which is the standard Google package for doing really AI, machine learning, which is machine learning. For those of you who had my AI class, and you can see that a lot of what you do is the same in AI as it is in graphics. It's dot products, it's matrix multiplications. So TensorFlow is a library that interfaces with Python, and TensorFlow is built to use TPUs. That's why it's called TensorFlow, right? Everything it's dealing with are tensors. So yeah, there are libraries that you can hook into that allow you to use the parallelism from Python if you've got the special purpose hardware to support it. Another thing that you can do, another reason, I'll jump down here to the third one, is you need to know about matrices, because if you want to use Direct3D or its predecessor DirectX, or you want to use OpenGL, they use matrices, and so you need to understand them. And that's another reason why I took 20 minutes to talk about the differences between point times matrix, matrix times point, because when you look at the matrix, I don't want you to be confused and go, but this matrix is not the same as the one that Mike told me. Because it depends on what system you're using, what assumptions they're making. But the map will still work out. Finally, another reason is to create a composite matrix. You can use the idea of composite matrices even if you don't have any special purpose hardware at all. Even if you don't have any kind of a graphical processing unit, you can still do a composite matrix. And we're going to look at an example of a composite matrix in a moment. But it allows you to do multiple operations in one step. Is what a composite matrix will do. Okay. Critical to all of this is dramatically speeding up computations, because the more computations you can do, the more detailed your models can be, the more polygons, the smaller those polygons, and the higher the frame rate. Now, we just talked about how the matrix notation allows for parallelism. Again, the hardware, the GPU or the TPU allows you to do the matrix multiplication of dot products in parallel. We're not going to get into the hardware details. I'm not a hardware guy. But again, if you think about your code in equation format, you're going to have to do the first equation, the second equation, the next equation, etc., and that's sequential. So what do I say here? Like if you're doing a rotation for a point, that would involve sequentially computing the x rotated value like you did in your homework or in your program, and then from the original x, and then the rotated y value from the original y, and finally the rotated z from the original z. So if you've got 1,000 vertices, the three equations, one for x, one for y, and one for z, you're doing 3,000 sequential computations. But if you're doing it with a matrix, you do 1,000. Right, you're doing 1/3 of the work, so that's a big speed up right there. So that's why we're doing that. I did some von Neumann machines for a paragraph. I shouldn't, because we wouldn't have the world we live in without von Neumann machines. When I say von Neumann machine, I just mean a computer with a CPU, a memory, and a long-term storage. Okay, so what is this composite matrix of which you speak, Mike? Well, if you'll go back and you'll remember, we did an in-place 2D rotation. And we worked through this last time, where we had our little blue triangle and we moved it to the origin, and then we rotated it by 90 degrees, and then we moved the rotated triangle back. And so the little thing in gray is where the original triangle was, and the one in dashed green is what it turns out to be. We did an in-place rotation. And there was much screaming and gnashing of teeth, because you could say, well, it wasn't in place because you did 3 steps. And I said, well, but you don't have to show what's going on in these steps. Just start with where it was and only show it after you've done all 3 things. And that was good enough for the last lecture, because it was true, right? We took the points and we ground it through the equations, right? This is giving us the translated to the origin points. So we take in our points, we plug it into these equations, we get the translated points. I did a 90 degrees counterclockwise rotation, so I hear the formulas for that. So these translated points become these now translated and rotated points. And then they go into this third equation, and out comes your final points. Well, if we express these not as equations, but as equivalent matrices, so x minus 3, y minus 2, this is the equation format that we just used right up here. Nothing changed. These are exactly the same equations. All right, I'm just repeating them here. So these are the equations for translation, the equations for 90 degrees counterclockwise rotation around z, and when viewed from minus z, and the translation back, same equations. They would be these 3 matrices, right, like we just talked about. One of the nice things about matrices that all have the same dimensionality, the same number of rows and columns, which these do, is you can multiply them together. So we can take the first matrix and the second matrix, and we can multiply them together to get a composite matrix that represents both the translation to the origin and the rotation. And then we can take this puppy and multiply it times a matrix that gets you back to the original point. Multiply these and you get this matrix here. This matrix represents moving the reference point to the origin, doing the rotation, and moving the reference point back. This one matrix does all 3 of these things. Don't believe me? Take the original points, throw them through these matrices, you get the translated points. These input points give you the same output points that we got by going through this 3-step process here. It's 2, 2 gives you 3, 1. 3, 3 gives you 2, 2. 4, 2 gives you 3, 3. And 2, 2 gives you 3, 1. 3, 3 gives you 2, 2. 4, 2 gives you 3, 3. It's exactly the same thing. Yeah, you're carrying these ones along, which you ignore, but it's exactly the same thing. And so now it really will happen in one step. You compute the composite matrix. Yeah, you got to do these matrix multiplications, but think about if you got 10,000 points, right? You can now, instead of doing the 10,000, I'm going to move my points to the origin, right? And remember, each of those has 3 things underneath them: the X, Y, and Z. So I'm going to do 10,000 of these calculations to move to the origin. Each of those calculations involves an X, a Y, and a Z. I'm going to do 10,000 of them to do the rotation. Each of those involve 3 substeps, X, Y, and Z. And then I'm going to do 10,000 to move it back, and each of those include an X, a Y, and a Z computation. Well, now, if I do a composite matrix, instead of doing, 30,000, 10,000 points times 3 operations, right? 30,000. I'm only doing 10,000. And each of those steps is faster because you're calculating the X, the Y, and the Z in parallel rather than sequentially. So really you're getting about a factor of 9 speed up here, right? By using both the fact that matrices do work in parallel and the fact that you're building a composite matrix. Okay, I see that I'm at my time limit. We're going to pick it up here next time, and we're going to work through one more example that's more detailed. It's a 7-step example, but it's something that frequently happens in computer graphics where we want to rotate points around an arbitrary line in space, not a particular axis, but some arbitrary line. Very common operation. Requires 7 steps, and we will talk about it, and we will derive the composite matrix for it, which will cause a massive speed up in the time to do this. Okay, I'm going to stop the recording here. If there are any questions, I'll be happy to entertain them. Appreciate it. Hold on, let me see if I can. Okay. All right, guys. I'll see you all on Friday. But you guys are doing presentations on Friday, right? Y'all are doing presentations on Friday. I'm not talking. You guys are. I'll see you guys then. Bye-bye.